Alright, in this video we're looking at exponential growth and decay. The big idea here is that we have many situations where a quantity increases or decreases at a rate proportional to the quantity itself. And there are a wide variety of applications for this. But what that means is that they're all modeled with this kind of differential equation. The change in y with respect to time is equal to some constant times y, the amount that's actually there. So the change in y is proportional to how much is there, with the initial condition that y is equal to y initial at time 0. And so if we solve this, we have a function that models all mathematical situations where a quantity increases or decreases at a rate proportional to itself. And so we're going to go ahead and do that. We're going to take this differential equation with this initial condition and go ahead and solve it and see what kind of model we end up with. So we've got dy dt is equal to k times y. And we're going to solve this using separation. So I'm going to get all my y's and dy's on one side and everything else on the other side. And now I'm going to integrate both sides of this equation. That gives us the natural log of the absolute value of y is equal to kt plus constant. And then we raise both sides of this equation e to that power. And so we're going to have e to the natural log of the absolute value of y is equal to e to the kt plus c. On the left-hand side, this is just going to be the absolute value of y. And on the right, we're going to simplify this a little bit. It's e to the kt times e to the c using basic exponent properties. And then e to a constant is just another constant. So this will turn into the absolute value of y equals c e to the kt. And I'm going to absorb that absolute value into the constant, and so we have the equation y equals c e to the kt. And now we're going to apply to that the initial condition to find the value of c. So y equals y sub 0 when t equals 0. So in essence, our constant is going to be y initial. And so we've got y equals y sub 0 e to the kt. This is the exponential growth and decay model. Anything that has a change in its amount based off the actual amount that's there can be modeled using this scenario. All right, let's continue on. And we'll look at, this reiterates the equation that we just found. One of the ways that we applied this in pre-calculus was you've seen this formula for continuous compounding of interest. You've also seen this related formula for various numbers of compounding periods. And so we're going to look at example 1 here, where we're going to find some values based off of these two models. They're both based off of example 1's stem here. Suppose you deposit $5,000 in an account that pays 3.8%. How much will you earn in 5 years if the interest is compounded? And now we're going to look at a variety of ways. First, continuously. In order to do it continuously, we're going to use the continuous compounding model. So the amount that we're going to have, P, is equal to the amount that we deposited, the initial amount in the account, times e to the RT. The R in this case is 0.038. We have to change that percent into decimal. And the time is 5 years. And so to find our principal, I'm going to break out my calculator. And I'm going to take 5,000 times e to the 0.038 times 5. And that tells me that if I'm compounding continuously, I'm going to have $6,046.25. at the end of the 5-year period. All right, next, let's do monthly. Now, if we're doing monthly, we're going to use this equation up here for k compounding periods. So we're going to have P equals 5,000 times 1 plus the rate, which is 3.8%, divided by the number of compounding periods. Since we're compounding monthly, there are 12 compounding periods in a year. And we're going to raise that to the k times t power. Excuse me. And the number of compounding periods is 12, and the number of years is 5. And once again, I have this set up, and now I'm just going to turn to my handy-dandy calculator, and I'm going to take 5,000 times quantity 1 plus 0.038 over 12 raised to the 12 times 5 power, and we should have $6,044.43. And lastly, we're going to do it quarterly, which means 4 times a year, so our number of compounding periods is going to be 4. Set up my formula again. And then I'm going to go ahead and calculate. Got 5,000 times quantity 1 plus 0.038 over 4 raised to the 4 times 5 power. And I'm going to have $6,040.83. $6,040.83. Okay, so that's one of the applications that we could have based off of the law of exponential change. Come back next time, you'll see we're going to look at another application of this law of exponential change in the remainder of this lesson. All right, see you next time.